We have the quorum to start. Okay. So, a few questions to you guys. What did we learn yesterday? What did we learn yesterday? Just put that in the chat. What did we learn yesterday? Yesterday, in the sense, the Friday. You all forgot. We talked about binomial distribution. Are you with me? So, what is the probability value? What is the formula for the probability? We know probability, what this is nothing but your probability mass function, because we are talking about discrete random variables. In that, we talked about Bernoulli distribution, and then we talked about binomial distribution. Now we will complete little bit left out binomial distribution part, and then we move to Poisson distribution. From there we move to normal distribution. Okay. So what is the probability mass function for binomial distribution? When x equals to r, this is NCR p to the power of r multiplied by 1 minus p to the power of n minus r. This is what we learned on Friday. Okay. So binomial distribution is basically, okay, what we can do is, it is nothing, what are the conditions, what are the assumptions that we have for the binomial distribution? The assumptions that we have written down on at the end of the class. I'm going there. See here, the total number of trails fixed, that is n is fixed. Each trail is a binary. Okay, that means let me write it here itself. Each trail is a Bernoulli, right? And the probability of success is P, and same in all trails. These are the three assumptions of this binomial distribution, or rather we can say the conditions of binomial distribution. So when I say x is a binomial random variable, sorry, yeah, x is a binomial random variable. This is nothing but, it is sum of all, suppose you have n trials, you have sum of all n Bernoulli random variables. Is there any doubt or any question in making in this statement which I made just now? That means I can say if I treat each trial as one Bernoulli, my x equals to x1 plus x2 plus up to xn. Okay, every trial, the probability will be, because I am using the word Bernoulli, okay, so the values are going to be success or failure. That is what Bernoulli means, right? Right? Please respond, everyone. You need to understand this point, otherwise no point in continuing. Are you with me? Did you get what I'm trying to say? When the sum of Bernoulli random variables is going to result into your binomial distribution. Please keep this in mind. In Bernoulli, everything is success or failure. That is, it is always binary. When it is binary, it is represented as 0 and 1. And the probability of this particular your random variable happening is going to be P. P stands for your probability, and it is a constant across all the trials. Here also it is 0, 1. Here also it is 0, 1. And P is probability. P is the probability of what? Probability of success, and is constant across all the trials. Is that making sense to you guys? Please respond before I move on to the next step. Now there are two things which we did not learn on Friday. One is the expected value of my Bernoulli, as well as not Bernoulli, expected value of my binomial. What is the expected value? Expected value of x. From the above definition, I have to write it like this. Am I making sense? Now expand this. Expected value of x1, expected value of x2, up to expected value of xn. What is the expected value of x1? x1 is a Bernoulli. We have already seen the value of expected value of Bernoulli random variable, which is nothing but p. Same case here, p. So like this, it goes up to here, p, which is nothing but, if there are n p's, this is going to be, resultant 2 is going to be np. Please note down, you need to remember this. Expected value of x for Bernoulli is p, whereas expected value of binomial is nothing but np. You have to remember this. Very, very important formula. Similarly, variance of x. Same theory. x1 plus x2 plus up to xn. If I expand this, this becomes, goes up to xn. What is the expected value of x when it is a Bernoulli? When it is a Bernoulli, this is nothing but p into 1 minus p is the variance of the Bernoulli. We derived this on Friday, not Friday, on Thursday. Plus p into 1 minus p. Like this, it goes up to p into 1 minus p. That means, so n times it repeated. So it is nothing but n into p into 1 minus p. So variance of x for binomial distribution is np into 1 minus p. Remember. Any questions till this point, my dear friends? Did you understand this concept, or you did not understand anything about it? Hello, others. What happened to Kutik? Arvind? Looks like blank faces now. Are we? Guys, I'm asking again and again because I don't learn to say yes. Okay, I wanted you to really understand the subject. Okay, can I say Vx once again? Let me go back into your class of 26. See here in the class 26, what we have done is we derived an equation for this is the Bernoulli. For the variance, we have come up with this formula P into 1 minus P. This is for Bernoulli. When X follows Bernoulli, what is the parameter? The parameter it takes is P. The variance of X is nothing but 1 P into 1 minus P. How we did it? Using the formula E x square minus E of X whole square. Whereas here this probability is P. This is also probability P. So P minus P square nothing but P into 1 minus P. This is how this is how we got P into 1 minus P as a variance value for the Bernoulli distribution. Okay, Arvind? Now we are talking about binomial. Binomial is nothing but the sum of Bernoulli's is nothing but binomial. Right? Here, that's what I said. Sum of all Bernoulli random variables is nothing but your binomial. Hope this is clear, Arvind? Okay. That's why you should not get confused the names Bernoulli, binomial, normal. You have to be familiar with all these things. From here onward, subject becomes little. This distributions basically will be little bit confusing to you guys, but it's okay. But after that, it is going to be really fantastic, very interesting. Subject is going to be very interesting. But these distributions probably you get confused or you may not understand, mainly because if you try to read material in or go to any book, you will only see these formulas. Okay, nobody will explain you with the concept and applicability how this has come and in what way you can where you can what is the meaning of this. Okay, that's why you have to listen to the my audio file again, so that you will once this and you get this right, then it will be very easy for you. There are few things which I wanted to remind you here. Okay, this is out of the topic discussion. There are three words which are very frequently used. One is exactly. Second, at least. Third, at most. These three terms are very frequently used in probability subject. Okay. What it means exactly means something like this. Probability of X equals to R. This dimension is this. This is exactly. Okay. At least means probability of X greater than or equals to R. At most, probability of X less than or equals to R. Okay, remember these symbols. This is at least. This is at most. So when we will be talking about when probability of X equals to 1, meaning we are talking about exactly what is the probability of my random variable when it is having the value equals to 1, exactly 1. That is what exactly means. Are you with me, friends? Okay. Now, greater than or equal to means at least. That means this is the minimum value. In this situation, R is the minimum value. That means you have to meet this condition, and that is the minimum possibility or minimum occurrence situation. Okay. At most means maximum. This is the maximum here. This is the maximum condition. This is the minimum condition. Okay. Let's elaborate a little bit about this, because you keep getting these terms going forward very frequently. So you need to understand this. Suppose you have x taking the values 0, 1 to up to n. So now probability of x equals to 0 plus probability when x equals to 1 plus blah 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 up to probability when x equals to n equals to how much? What is the value here? Can anyone tell me what is the value of sum of all the probabilities? Probability, sum of all probabilities will always result into 1. In general, sum of all probabilities equals to 1. Okay. This way of adding the values, okay, this way of adding the values is called cumulative probability. This is called cumulative probability. This is another term, guys. Please remember. Cumulative probability. Okay. Is always represented as capital F R. This is how it is represented as. Let's not worry about, but just listen to this term. We will see in detail once we get into the continuous random variables. Okay. This is cumulative probability. Now let us write few equations for your better understanding of these three terms. Probability of x less than or equals to. Keep this in mind. Probability of x less than or equal to 2. How do I write? Less than or equals to. Less than stands for that is the maximum. You see here I said this maximum. So this I can write it as probability of my x equals to 0 plus probability of x is equal to 1 plus probability of x equals to 2. Friends, are you with me? Any difficulty in understanding this? Please respond. Any difficulty in understanding this? Clear? Okay. So in other words, I can write this as f of 2. That means this is the cumulative probability. P of x less than 2 equals to capital F of 2. Okay. This is another way of representation. This is one way. This is the actual definition. From again, there is another one. The sum of all the probabilities are equals to 1. Okay. Then what I can write this as 1 minus probability of x greater than 2. Can I say this? That is what it is, right? less than or equal to. So 1 minus p x greater than 2 should be the same. This and this are same. They are same. Right? Did you get what I'm trying to say? Please respond. Yes. There is a catch here, guys. You need to understand this. Okay. Oh, this one. What is x is greater than 2? X has the values of, my dear friend. Here, x has the values of 0, 1, 2, 3, 4, something like this, up to n. So, x greater than 2, what is the next immediate value? There is no 2.1, there is no 2.3, there is no 2.5. The next immediate value is 3. So, in another words, I can write this as, am I making sense? In this case, okay, sorry, if let's say if n equals to 3, there are only up to 3 only, then I can end it here. Otherwise, I can use it for n times the rest of the things. Are you with me? If I make n equal to 3, this is the definition. If it is not n, if it continues to the up to n, then this term will have something like this. Up to n, it goes up to n, then x is equal to n. Friends, are you with me? Okay, let me check how much you really understood about this. Let me keep your understanding part. I am okay to spend one more class extra. That's fine. But this difference, you need to understand this. Now tell me, write down in the chat, how do you write this? X less than or equal to 1. That means this is the maximum value. Yes. Kritik, why are you writing privately? Put it in everyone so that everyone can see it. Even if you do mistakes, what is the problem? This is nothing but 1 minus P of x equal to 2 plus P of x equal to 3. Can I write like this? There are many ways. There are many ways you can write it. Just see this pattern. Right? So remember, this is always at most. In this context, I have taken n equals to 3. I said, okay, in the top here. Because in this context, if I take n equals to 3, here also, if I want to calculate this is how I can write it. Or simply you can say this. Fair enough, right? Probability of x equals to 0 plus probability of x equals to 1. Can I say this? Honestly, yes, this is true. Are you with me, friends? Okay, wonderful. Okay, let us move on to something called Poisson distribution. This is the third distribution in discrete random variables. So this is again simply from your understanding. I just shared what what is the meaning of these this way of writing the this way of representation. Sorry. Okay, you need to understand. You need to keep this in mind. Then you will know how to apply the principles. Then you can easily correlate yourself to the when you are dealing with any business problem. Okay, you might be thinking how much we have to learn these these things. Still fundamentals going on. 28 class. Still we are going to the data science fundamentals. Answer is yes, my dear friend. You have to go through. Okay, there are still another 12 more classes that you have to go through from a fundamentals perspective before we step into actual data science mathematical modeling. Okay, so in fact I take almost 4 to 5 months every four, almost close about 100 to 120 classes only from the fundamentals perspective. 3 months I teach continuously to get this registered in people's mind. Okay, but that effort is worth. After that they come back and then later on they will, I simply give more, I only teach 3 techniques in the mathematical modeling side, and then rest of the techniques I tell the names, guys, please go ahead and explore yourself. Within 1 month they come back and say, sir, we are good at, we understood what these logics are or these mathematical models are, and they'll start coding it beautifully in R and Python. So that's the reason I'm spending enough amount of time and doing it very slowly, mainly because these are the very fundamentals which you need to have absolute clarity. If you don't have it, you may be the expert in Python and R. It's of no use. And unfortunately, many of the engineering colleges, they always think that teaching in the Python and writing the programs in Python is considered as a data science. They take some small examples and they'll try to build models. They'll try to copy some commands from the libraries that were given, and they will show you the output and they say, yeah, we did a project. Our students have done the project. I laugh at them. I said, you guys don't even know what the data science is. Okay, jokes apart. Let's look at the Poisson distribution. It's not poison, okay? It's not going to kill anybody. It's very, 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 very useful. Okay. It is also called as approximated value of binomial distribution. Let me write it so that you will remember. It is also called as approximated approximated value of binomial distribution. Why it is approximated, we'll see. Second important point, when do you apply such kind of a data distribution? When you are having a business problem in such a way that your number of records, your n, is very, 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 very large, and the probability of occurring the event is very, very, very small. Let me write it. It should be applied when p is very, very small and n is very large. When you are satisfying this type of condition, that is when you actually apply by Poisson distribution. Okay. And another important aspect of this is there is a time period is also attached to this Poisson distribution. Okay. That is the another important point. This time. Then you use Poisson distribution. I just pause for 30 seconds. I just read through this. It is also called as approximated value of binomial distribution. It should be applied when your probability of that event occurring is very small, and when your total number of experiments are going to be your records are going to be pretty large. Your N is very large, and it is confined to a time period. Okay, so let me draw a simple. This is a circle. Okay, so this is JNTU circle, let's say, or Amirpet circle. JNTU traffic signal. Okay, you see people coming from all the directions. Okay, and people come and go in these four directions. Now you are trying to solve a problem for the policeman. What is the problem here? They wanted to understand how many people are jumping the signal. What is the problem statement? The problem statement, jumping the signal. Now question to you. I'm asking a question to you. How many people do you think can actually jump the signal? Can anyone answer this question to me? Please answer my question, guys, my dear friends. Ravi says none. Do you think people don't jump the signal? People jump the signal. Then you should ask my question whether I'm asking the right question or not. So your next question is, it is very difficult. It is an open-ended kind of a question. How many people are going to jump the signal? Is it for 1 day? Is it for 1 hour? Is it for 3 hours? Or is it 5 hours? Or 5 o'clock? Or 6 o'clock? Or 10 a.m. Or 3 months, 3 days? Or 40 days? Or 60 days? Or 1 year? So the question that I'm asking is not right. It's not a question of right or wrong, but the question it is that you have to confine. If I say between 8 a.m. to 9 a.m., how many people are going to jump the signal? Yes, you will have an answer, because you can stand there, right? You can stand here. You can basically actually note down within this particular time frame how many people are actually jumping the signal. If I don't do that, if I don't limit myself to toward this particular time frame, the N is going to be here pretty large. because there's so many people will be traveling in this area at this time, at any time of the day. If many people will be traveling, so out of, let's say, 10,000 people have actually crossed through this junction, maybe one or two people might have jumped the signal. Do you see the point which I'm trying to drive towards? Your n is very large, whereas the probability of jumping the signal is very, very small, because number of people who jump the signal are very, very small. From that, how do I calculate probability? Total number of favorable items, number of favorable items to total number of favorable items. Your n is very large, and your number of the favorable item number is very small. The probability is negligible. In fact, it's very, very small. So here your n is basically big mass, huge mass. Okay. Now the question comes, in Poisson distribution, we don't calculate P. Why? Whether I calculate the P or not, when P is very, very small, what is the point in me calculating the probability? Is the first question should come into your mind. That is mainly because the data that I have is very large. Okay. So remember, whenever you are trying to apply the Poisson distribution, you don't look at the probability. I am not worried about probability, because collecting of the entire data is very, the data that we have is very large. Another example, number of flights crashed in a year. Then it's very large. So many flights will be flying. How many flights are really going to crash? The probability is very less. In fact, you want the probability should be 0. Otherwise, do you think you will board the flight which is going to crash? Right? Earthquakes in a year in Hyderabad. What is the probability? Very, very less, remote. So your X random variable, the jumping of the signal, basically it's like this. Your X is jumping of the signal, This is what I have written here. Here is nothing but, okay, x1 plus x2 up to what? Up to infinity. Probably if I collect the data for years together, my number, this number also, jumping the signal number also goes little up, but still my N is very large. Okay. In such a situation, because the P is very large, okay, so there is an alternative parameter called lambda. This is called lambda, which is also called as an alternate parameter. Okay, an alternate parameter. We will define what this alternate parameter is. This alternate parameter is something similar to average number of incidents per scope. I'll say this is defined as average of number of incidents per any given scope. This scope can change like anything. In such a situation, in Poisson distribution, your probability mass function is calculated with something like this. P probability of x is equal to R equals to e to the power of minus lambda into lambda to the power of r divided by r factorial, where your e value is 2.71, whatever it is, 8 or whatever, up to so many decisions. Okay. Now the question comes. Oh my goodness, Hari, we understood Bernoulli equation, Bernoulli distribution, we understood binomial distribution. Poisson is something not getting into the head. So when we talked about discrete random variables, we talked about two types of discrete random variables. What are, do you remember? Classification. What is the another one? Anyone? Anyone, can you answer me? What is the other one? You are not for studying the subject. Count. For the classification, you use binomial. For the count, you use Poisson. Remember this in your head. Okay? Now, because we know for probability mass function, now you need to know what will be the value of expected value of x and what will be the values for my variance. These are the two things which you need to know for the Poisson distribution. Okay, so let us look at the definition of my x random variable. X is a Poisson random variable which takes the values from 0, 1, 2 up to, it may go to infinity, where my n is very large. That means my n is also goes to infinity. How do I represent? X follows Poisson with the parameter lambda. Remember this. This symbol stands for follows. So now, from this point of view, my definition is going to be expected x is going to be the same thing. Each one is again kind of a Bernoulli, x1 plus x2 plus up to xn. Sorry, not xn, up to it goes to infinity, right? This is what we said. It goes up to infinity. This is exactly similar to binomial. Do you agree this point? Only thing is binomial is only up to n, where n is defined. N is not infinity. Here it is, n is in place of n we have infinity. Hence it is called as approximated value of binomial distribution. Okay, so we already calculated this for binomial distribution. So what is the value of this one? This value of this one is going to be NP. We have already just now few minutes back we calculated this. What is this NP basically? This is nothing but an average. So this they equated to lambda. Similarly, your variance of x is, we have seen that as a NP into 1 minus p in binomial situation. In this context, okay, now NP I will not, we are substituting this as lambda into 1 minus p. Because my p is very small, that means this is 0, this becomes lambda. So variance is also becoming lambda. What is this lambda? Lambda is an alternative, is a parameter which you will be calculating using average of the total number of incident per scope. It's a different parameter. Why are we trying to make gimmick around or trying to make circus around this is basically because our p is going to be very, very small. Since the p is very, very small, we are trying to find out how we can address the problem. So lambda is the way using which we can actually address the problem. Remember, expected value of x equals to variance of x equals to lambda in Poisson distribution with your probability mass function equals to e to the power of minus lambda into lambda to the power of r divided by r factorial. Friends, are you with me? Okay. So you want to show me an example for this? We have shown this. We will see this part. Okay. Day-to-day life, number of persons hired in a company. You have a position available. So number of interviews are going on. Okay. Now you want to calculate, okay, or you want to find out how many persons are going to be hired in a company. Okay. So in Poisson distribution, I'm interested on selected. How many people I select? I don't know. My N is large. I may be calling for open drive or walk-in drive where 100,000 people coming in. But I am interested in selected candidate. Are you with me? I'm interested in the selected item. So what is the probability of that selected item is pretty small. But that probability, instead of probability, I look at the count of how many people got selected. That is your lambda. That how many is nothing but an average. Okay, suppose you have 100 positions and you have data points say for 75 people. And see here probability is what you need to look at is that's a good question you asked for Kutik. What is the probability of one person getting selected? Let us assume that out of 50 people, you are able to select one candidate. That is the history of your organization. That is the history of your organization. So 1 by 50 is your probability P. Now the question comes in, if I want to hire 10 positions, how many people I should interview? Is the Poisson distribution. Are you with me? So what do you do? Your probability says, let's say 0.015 something, right? So I'm not, now what I do is I will look at the lambda, which is average number of people selected per skill set or average number of people selected in the company. Are you with me? Kritik, did you get what I'm trying to say? That is called Poisson distribution. Suppose if the probability of you hiring in your company is 0.1, there are some companies, they will do, let's say they do a thorough interview, 7 rounds interview, 8 rounds interview, 10 rounds of interview, maybe if the time allows, they will even interview 100 rounds also. There are some companies which they think that they are great people. The probability is, let's say 0.1. Now the question is, I'm interested in how many get selected. If I want to fulfill, let's say 10 positions in such a situation, How many people I should be able to call or interview is your Poisson distribution. Are you with me, my dear friend? Okay, wonderful. Clear? Now the question comes. I'll slightly twist the same situation. I'm taking the jumping of the signal. Okay. I want to find a person who jumped the signal at Amirpet or at JNTU. In the first scenario, in the Poisson distribution, I'm more interested in what is the probability of people jump the signal. Okay. Out of my n is very large and probability is very small. So within the given interval, let's say for about 1 hour, 8 to 9, you may find 10 people who is jumping the signal. You are more interested in that. No, you are not interested in the 10 people who jump the signal. You are interested in what is the rate at which the people are jumping it. But if you are interested in number, how many people actually jump the signal, that is called geometric progression. Another example, KCR recently, adopt a village called Gangadevarapalli or something, I don't remember. Hey, let's say they want, KCR wanted a bore to be drilled over there in the village, and then they want to construct a tank over there. Now, KCR asked the authorities to give him the budget about how much money that he would like to give it to or allocate for Gangadevarapalli to just drill a bore. When I say drill a bore, you simply can't look at some place and just drill a bore and then you go back and tell KCR, sir, there is no water. And moreover, Gangadevarapalli is notorious for not having the water, the groundwater level is very, very poor. Now what they do is geometric progression means what is the success rate of one bore? They are interested in that. What is the success rate of one bore? Let's say in the previous history, they might have drilled 10 bores. After 10 bores, one bore was successful. In such a situation, if I want to drill a one bore, I have to go for 10 drills. That means I need to budget 10 drills, 10 bore wells cost and give it to KCR. That is what the geometric progression is all about. Geometric progression random variables always denotes about the number of people, whereas the Poisson looks at it, how many people are, I mean, is there any occurrence of people who are jumping the signal during a given time frame, or I'm focusing more on number of people in a given time frame. Here in geometric progression, it is not about within the timeline, it is about the success rate that decides how I will be addressing the problem. Am I clear? Is it clear to you, my dear friends? So in Poisson distribution, your random variable denotes number of times an event is occurring in an interval of time. Remember this. Let me repeat. The situation here is X, your random variable, when do you say a random variable is a Poisson distribution, follows a Poisson distribution? When number of times an event occurs in an interval of time, when you are focusing that time you have to apply Poisson distribution. But when you are focusing at the success rate, then you need to jump onto the geometric progression, because there you are concerned about actual number. Are you with me, my dear friends? Okay. So with that said, we are done with the discrete random variable probability data distributions. We have looked into the Bernoulli, we looked into the binomial, we looked into the Poisson, we looked into the geometric progression. Okay, and in the geometric progression, well, okay, just remember this formula, it will be useful to you. In geometric progression, your probability mass function is written something like this. It is represented as small fx, which is nothing but probability of x at small x. That means these are x takes the values. This is nothing but 1 minus p to the power of x minus 1 multiplied by p, where my x stands with 1 comma 2 comma like this, etc. Whereas in Poisson distribution, even 0 is also possible. But in geometric progression, 1 is minimum. That means success, that is minimum. Okay. Okay. With that said, we are done with, or rather, I say we have covered only 4 data distributions for discrete random variables. I think this is good enough. Tomorrow we will jump onto the continuous random variables. And predominantly, I would like to take you through uniform distribution as well as the normal distribution. Let us focus more on normal distribution, because end of the day, any data that you are getting from anywhere, always the focus will be how we can translate the data into normal distribution. Why we do that? Because we have enough understanding, or we have enough tools using which we can actually determine the probability function for normal distributed data. That's why so much of attention will be given to normal distribution, and we will spend a lot of time over there about this, understanding this concept, followed by your something called central limit theorem, which is very popular. After the central limit theorem, we will actually step into the actual original data science subject. Till then, it is all about trying to recall your understanding or mathematics or statistics, whatever that you have learned in the previous your education system, or you might have not even learnt about it. That's all fine. So from Thursday onwards, we will actually step into the data science. Okay. Thank you, guys. I'm sorry I've taken 2 more minutes extra. See you tomorrow.